Bismillahirrahmanirrahim. In our previous lecture, we were discussing eigenvalues and eigenvectors of second order tensor, and we have discussed one example for eigenvalues and eigenvectors in which we have taken a tensor whose eigenvalues are repeated, and you have seen that we have calculated eigenvectors, three linearly independent eigenvectors. Today we will start with an example which is in which a tensor T is given, whose first row is 2 0 0, second is 0 2 0, and third is 0 0 3. We have to calculate its eigenvalues and eigenvectors. So this is the characteristic equation. From here we can have eigenvalues. One is λ3 and other two are repeated, 2 2. Now for lambda is equal to 3, we will calculate eigenvector. For lambda is equal to 3, we have to go back on page 34, equation number 4, where we will use lambda is equal to 3, 2 minus t1 1 is 2, 2 minus 3 into alpha 1 plus 0 into alpha 2 plus 0 into alpha 3, because t1 2 0 and t1 3 0. Similarly, second equation t2 1 0 plus t2 2 minus lambda is 3, 2 minus 3 t2 2 is 2 into alpha 2 plus 0 is equal to 0. Third row 0 plus 0, because t3 1 and t3 2 they both are 0, plus t3 3 minus lambda, t3 3 is 3 minus 3 into alpha 3 equals to 0. Now from first equation alpha 1 is 0, from second equation alpha 2 is 0, and from third equation alpha 3 is arbitrary, because from third equation is giving us 0 into alpha 3 equals to 0. So this equation will be satisfied for any value of alpha 3, because it is multiplying with 0. So it means that alpha 3 is arbitrary, so we can take any value of alpha 3. So what would be the eigenvector? We know that n is alpha 1 e1 plus alpha 2 e2 plus alpha 3 e3. Alpha 1 alpha 2 are 0, alpha 3 as it is, so eigenvector is alpha 3 e3. So alpha 3 would be any value, so we have infinitely many eigenvectors by changing the value of alpha 3. So to find the unit eigenvectors we will have to use this equation. This is the condition of unity. Unity means that unit length of this n dot n equals to 1. So alpha 1 0, alpha 2 0, and alpha 3 would be plus minus 1. So we have n is equal to plus minus 3 unit eigenvectors, plus minus 3. Now for lambda is equal to 2, for lambda is equal to, we will again use equation number 4, page 34, to find the eigenvectors. So 2 minus 2, alpha 1 plus 0, alpha 2 plus 0, alpha 3 is equal to 0. 0 into alpha 1 plus 2 minus 2, alpha 2 plus 0, alpha 3 is 0, alpha 1 plus 0, alpha 2 plus 3 minus 2 into alpha 3 equal to 0. Now we can see that alpha 3 is 0 from this equation, and alpha 1 and alpha 2 are arbitrary. Why they are arbitrary? Because from 1 we have 0 times alpha 1 equals to 0, and from 2 we have 0 times alpha 2 equals to 0. So it means that equation 1 and equation 2 are satisfying with any values of alpha 1 and alpha 2 respectively, because for any value of alpha 1 this equation will be satisfied, for any value of alpha 2 this equation will be satisfied. So it means that alpha 1 and alpha 2, they both are arbitrary. So what would be the eigenvector? This would be the eigenvector, alpha 1 e1 plus alpha 2 e2 plus alpha 3. Alpha 3 is 0. So we have alpha 1 e1 plus alpha 2 e2. Any eigenvector lying in the plane x1 x2. Now to find unit eigenvectors we have to make use of this equation. This is alpha 1 square plus alpha 2 square plus alpha 3 square is equal to 0. As alpha 3 is 0, so we are left with only alpha 1 square plus alpha 2 square is equal to 1. So in particular we can have, if we take alpha 1 is equal to 0, alpha 1 is equal to 1 and alpha 2 is equal to 0, we have n is equal to e1 one eigenvector, and this is for n is equal to e2 another eigenvector. So it means that we have 3 eigenvectors which have length 1 and they are perpendicular with each other. One is this one, second one is this one, and third one you can have from here, n is equal to plus e3. 3 eigenvectors e1 e2 e3, they are perpendicular with each other and their length is 1. So we will do another example in which you will see that all eigenvalues are different. In first example, all eigenvalues are repeated. Second, there are only 2 repeated eigenvalues, one is different. And third, you will see that all the eigenvalues are different and we will find the corresponding eigenvectors. This is the characteristic equation for this tensor. Lambda is equal to 2 is one eigenvalue and other 2 eigenvalues are plus minus 5. So there are 3 eigenvalues, 2 plus 5 minus 5. Now we will have to calculate the corresponding eigenvectors for these 3 eigenvalues. No, we will make use of equation number 4 from page 34 for lambda 1 is equal to 2. This would be the first equation, this would be the second, and this would be the third. Now from first equation you can see that 0 alpha 1 equals to 0, these are 0. From second you have alpha 2 plus 4 alpha 3 equals to 0, and again from third 4 alpha 2 minus 5 alpha 3 equals to 0. Here you can see that this is homogeneous system. From this we can see that alpha 1 is arbitrary, and from here we have to calculate alpha 2 and alpha 3, and this is a homogeneous system, and you can see that its determinant is not equal to 0, and if you have homogeneous system determinant not equal to 0, then solution is only trivial, that is alpha 2 alpha 3 equals to 0. So eigenvector would be alpha 1 e1 alpha 1 e1. This is, from here you can have infinitely many eigenvectors by giving the value of alpha 1. For unit eigenvectors, you have to use this type of equation: alpha 1 square plus alpha 2 square plus alpha 3 square is equal to 1. So alpha 1 will be plus minus 1. So if you will use this value here, then you will have n is equal to plus minus e1. These are two unit eigenvectors. For eigenvalue lambda 1 is equal to 2. Now for lambda is equal to 5, for lambda is equal to 5, you will use this lambda is equal to 5 in equation number 4 of page 34. You will have this equation. This would be the second, this would be the third, and from first you can see that your alpha 1 equals to 0. 3 minus 3 alpha 1 equals to 0, so alpha 1 equals to 0. And let us see what happens when we solve these two equations. From here we have alpha 2 minus 2 alpha 3. From this equation we have again alpha 2 minus 2 alpha 3 equals to 0. So this is a homogeneous system but its determinant is 0. You can see that minus 2 plus 2 equals to 0. So this system will have infinitely many solutions in addition to its trivial solution, because you know that for homogeneous system trivial solution always exists. Now what is the eigenvector? This is the general form of eigenvector. You will use values of alpha 1, alpha 2 and alpha 3. 0, what alpha 3 as it is, and what is alpha 2? You can write alpha 2 in terms of alpha 3 from here. So it will be 2 times alpha 3 e2. So we can take alpha 3 as common and we are left with 2e2 plus e3 in parentheses. So eigenvector is alpha 3 into 2e2 plus e3. So we need to find unit eigenvectors. So we will use this equation again. We know that alpha 1 is 0, alpha 2 square plus alpha 3 is equal to 1. So we have this type of alpha 3, and then alpha 2 will be this. Alpha 3 you have used alpha 2 is equal to 2 alpha 3. So this is 4 alpha 3 square plus alpha 3 square is equal to 1. So alpha 3 is plus minus 1 or square root of 5, and alpha 2 is, as you know that alpha 2 is 2 times alpha 3, so alpha 2 will be plus minus 2 over under root 5. So this is the eigenvector. From here you have two eigenvectors, they are perpendicular, unit eigenvectors. Now similarly for lambda is equal to minus 5, you need to follow all the procedure which you have done for lambda is equal to plus 5. So by doing this you have alpha 1 0, and from this equation you have this, and again from this equation you have this, again alpha you have homogeneous system, infinitely many solution, and alpha 3 you can write alpha 3 in terms of alpha 2 or alpha 2 in terms of alpha 3. It depends on you that how you do the simplification of eigenvector. Now this is the general form. Put alpha 1 0, alpha 2 alpha 3, take the alpha 2 as common, and in the parenthesis we have e2 minus 2e3. Maybe I have missed something here. I have to complete this also, as I have done for lambda is equal to plus 5. No, it will be your exercise. You have to complete this. Similarly, as we have done here for unit eigenvector, you will see that you will have 2 unit eigenvectors for lambda is equal to -5, and you can then see that for this example in which all the eigenvalues are different, you have again 3 eigenvectors which are perpendicular with each other and they are unit. We will summarize all this in the next section. Now this is an example which you can see that our tensor is not symmetric. All the 3 examples which we have done before this, in which the tensor which we have used to find the eigenvalues and eigenvector, that tensor was symmetric. Now this is not symmetric. We will find eigenvalues and eigenvectors. We will see that when you will find eigenvalues, one eigenvalue is 1 and other 2 eigenvalues are complex conjugate of each other. Here you can see that we have done 3 examples with symmetric tensor, and you can see that all the eigenvalues are real. And when you have when you have a tensor which is not symmetric, then you can see that eigenvalues may be complex conjugate of each other. This is not necessary that you have always real eigenvalues. If your tensor is symmetric, then your eigenvalues will be real. Now add one thing more here. If your tensor is symmetric and real, then it is sure that your eigenvalues will be real. And if your tensor is not symmetric, then it is possible that some of your eigenvalues are complex conjugate of each other. For example, we have seen here that this is not symmetric and this has maximum 3 eigenvalues, so 2 are complex conjugate of each other. So what is the result? Result is, if you have real symmetric tensor, then all eigenvalues will be real. But if you have a tensor which is not symmetric or real, if it is not real, then it is possible that it would have only complex values. If there are 3 eigenvalues, then it is understood that one will be real and other 2 will be complex conjugate of each other. So for real symmetric tensor, we have all the eigenvalues real. So this is the counter example, that if you have a tensor which is not symmetric, then this tensor may have eigenvalues which are complex conjugate of each other. Now, principal values and principal directions of real symmetric tensor. So no, we are only supposing real symmetric tensor, real plus symmetric tensor, and we will talk about principal values and its principal directions. So this is a theorem that eigenvalues of real symmetric tensor are all real, as I was saying before this. For real symmetric tensor, eigenvalues are real. Thus, for real symmetric tensor, there always exist at least 3 real eigenvectors. You have seen in previous 3 examples. In all cases, either eigenvalues are repeated, 1 time repeat, 2 times repeated, or all repeated. Then you have 3 real eigenvectors, which we shall call as principal directions. Then the corresponding eigenvalues will be called as principal eigenvalues of tensor T. Which type of tensor? Real symmetric tensor. Real symmetric tensor eigenvalues are principal values and vectors are principal directions. And there exist at least three principal directions. Real. Now we shall prove that these 3 principal directions are mutually perpendicular. We shall prove that 3 principal directions are mutually perpendicular, as you have already seen in your previous examples. In all 3 examples we have 3 mutually perpendicular eigenvectors. We shall prove here. Suppose that we have 2 eigenvectors n1 and n2 corresponding to the eigenvalues lambda 1 and lambda 2 respectively. You can write this one, Tn1 equals to lambda 1 n1, Tn2 equals to lambda 2 n2. This is for eigenvector n1 with eigenvalue lambda 1. This is for eigenvector n2 with eigenvalue lambda 2. Now what is this? You are taking dot product of this with n2. So it would be n2 dot Tn1 equals to n2 dot lambda 1 n1, and take the dot product of n1 with this. What you have to show? You have to show that these 2 eigenvectors are perpendicular with each other. Now you have rewritten these 2 equations in the form of 1 and 2. We know that by the definition of transpose of a tensor you can write this. n1 is a vector, n2 is a vector, t is tensor. Then you can use definition of transpose of tensor t, and with the help of definition of transpose of tensor t, then you have this type of equation: n1 dot tn2 equals to n2 transpose of t n1. If you remember, you know that your tensor is symmetric, so you can use transpose of t equals to t. So it would be n1 dot tn2 equals to n2 dot tn1. So using this in these 2 equations 1 and 2, you can write this equation, because with the help of this you can see that left hand side of these 2 equations is same, then right hand sides will also be same, and you can take one side to another other side. From that you have lambda 1 minus lambda 2 and 1 dot n2. This would be the common, and in the parenthesis we have a lambda 1 minus lambda 2. Now if these eigenvalues are different, so it means that this product will be 0. If this dot product will be 0, this dot product will be 0, then we can see that these 2 are orthogonal with each other. Thus eigenvalues are distinct, then 3 principal directions are mutually perpendicular. Now If you have n1 and 2 eigenvectors, but eigenvalues are same, say lambda 1 is equal to lambda 2 is equal to lambda 3, and third eigenvalue is different, which we say lambda 3, and there will be corresponding eigenvector which we will say n3. Now what will happen if you have two eigenvectors n1 and n2? They are different but eigenvalues are same, lambda 1, lambda 2, lambda. Then by definition we can write this and this. We can write this thing: alpha and beta are scalar, then t of alpha n1 as eigenvector, alpha n1 is scalar multiple, plus n2 eigenvector, beta is the scalar multiple of n2. Now what we have to check? We will check whether this is an eigenvector or not. We can write with the help of linearity of tensor t, alpha into tn1 plus beta into tn2, tn1 lambda n1, tn2 lambda n2. So this would be this. So from here we can see that this is an eigenvector with eigenvalue lambda. And we are saying that n3 is eigenvector, and this for eigenvalue lambda 3, this would be perpendicular to this eigenvector which has eigenvalue lambda, whose corresponding eigenvalue is lambda. Why? Because using this case when eigenvalues are different, because here eigenvalue is lambda and eigenvector is this, and here eigenvalue is lambda 3 different from lambda, and eigenvector is n3. So n3 must be perpendicular on this with eigenvalue lambda 3. So it means that again we have at least 3 mutually perpendicular principal directions. This you have seen in your example in which two values are repeated. Second example. And third case, when all the eigenvalues are repeated. And you can see that by using equation of 4 on page 34, alpha 1, alpha 2, alpha 3 will have any value to satisfy that system of equation. So we have any vector as an eigenvector. So we can choose 3 perpendicular eigenvectors, which are basically principal directions. We have seen this in our first example. So what is the conclusion? This is the conclusion, that for every real symmetric tensor, there always exists at least one triad of principal directions which are mutually perpendicular. We know that for every real symmetric tensor, their eigenvalues are real, and we have also seen that there exists at least one triad of principal directions. One triad means that there exist at least 3 principal directions which are mutually perpendicular with each other. So please go through this lecture. We will discuss this tomorrow, inshallah. Thank you so much, and Allah Hafiz.